let's say that I give you two charges, so there are two electrostatic charges Q1 and Q2, and I tell you that they're spaced by some distance r, so r is just the total distance between the two charges, located on a set of three axes, x, y, and z. So I give you the location of Q1 and Q2, so they're given by these coordinates, and I want you to find the force that is applied by charge 1 onto charge 2. So basically the force that goes from charge 1 to charge 2. Now, by Coulomb's law, what we can do is we can set some constant k, and we know that the magnitude of the force should be equal to Q1 times Q2 over the distance squared. So basically this is an inverse square law, and it tells you that as the distance increases, the force is going to decrease by a factor of 1 over r squared. So basically the force is going to become very, very small as you increase the distance between the two charges. Now this only gives you the total magnitude of the force. If you actually wanted to find the force between the two, this would be a little bit more complicated. But we can actually use the tools we have learned so far, because we know that in order to give this quantity, so this is just a scalar quantity, if we want to turn it into a vector, so let's say f12, all we need to do is we need to multiply this magnitude by some unit vector. So the unit vector is not really going to change the magnitude here. The magnitude is going to stay the same, but it is going to give it a direction, and the direction we need in this case is the direction that points from charge 1 to charge 2. So it goes like this. So how do we go about doing that? Well, we know that this is just going to be given by the position vector. So how about we make a position vector in terms of your unit vector? So what we're going to do now is, we know that the unit vector is just going to be the vector r over its own magnitude. And we know that the magnitude is just going to correspond to the distance. So this is just going to be r. So if we plug this in here, it turns out that the force from applied by charge 1 onto charge 2 is going to be k q1 q2 r cubed, because we have 1 over r here times that, and then this is just going to multiply the vector r. So this is essentially what we're going to do in order to transform this scalar quantity into an actual vector. So we want to take a magnitude and have a magnitude and a direction, because that's how we would define forces. And this is much more useful because it encapsulates a lot more information than just this. If we just had this, well, we wouldn't really know in which direction the force is going, so the forces could actually be going in completely opposite directions, and physically that would have no meaning. It would make no sense. So this is why we need a direction. Okay, so how do we find this vector r? Well, there are different ways to approach it, but how about we use the same method that we used to begin with, which was, let's draw two vectors, one that goes from the origin to q1 and then from the origin to q2. So let's call this one r1, r2, and then this vector r is just going to be r2 minus r1. So let's just do that. Let's go down here. R1 is just going to be the coordinates of charge 1. So if we go up here, we define charge 1 at 2 minus 1, 3. So this vector is just going to be 2, minus 1, and 3. And then R2 is just going to be the coordinates of the second point. So that's 0, 2, and 2. So very straightforward. We have 0, 2, and 2. Alright, so that implies that our vector r is just going to be r2, so that's the endpoint, minus r1. And this is going to be equal to the following. So we take this minus that, so that's minus 2. And then we have r1, so that's going to be minus 1 here. So 2 minus minus 1, that's going to be 3. And then 2 minus 3, that's minus 1. So this is going to be the vector corresponding to that. And now we need to have the magnitude. So the magnitude is going to be this equals to square root of minus 2 squared plus 3 squared plus minus 1 squared. And this is going to give us the following. This is 4 plus 9, so that's 13, plus 1, that's 14. Square root of 14. And now we plug this back into our equation, so the force becomes K times whatever the charges are. We didn't specify it in the problem, but we don't really care about that. And this is going to be square root of 14 to the power of 3 times the vector. So this is going to be minus 2, 3, minus 1 newtons. So that's going to be our force vector. And you notice that essentially we have this magnitude here. Obviously this is going to scale it further, but we already took care of that by multiplying it by the magnitude here. But the interesting thing is that we just gave it a direction, and it so happens that that's the same direction as the vector r. Now you might be thinking, well, an electrostatic force is actually applied by both in both directions. So basically this exerts a force onto charge 2, and charge 2 exerts an equal force onto charge 1. So how do we represent that? Well, you can easily establish the relationship F from 1 to 2 equals to minus F from 2 to 1, because you know that F from 2 to 1 is just going to be the same thing here, but it's just going to have all the signs inverted. So it's going to be K Q1 Q2 over square root of 14 to the power 3 times 2 minus 3, 1, because it is going to be in the opposite direction, so you want basically to invert the signs here. And what's going to happen next is, if you want to make this exactly equal to this, all you need to do is multiply by -1, and that will give you the original vector again. So this is where this relationship basically comes from. So vectors are quite useful for calculating forces and all that, and we'll see in the next video that this can actually be extended to a lot of other applications, not just in electromagnetics, but also in statics and mechanics.